In this video, you're going to be able to calculate and learn how to calculate hydraulic gradients using nested piezometers. So first of all, what is a nested piezometer? I've drawn at the side here a bird's nest. So it's not a bird's nest. What it is a piezometer, which is a plastic, often plastic tube that goes into the ground. And it's used to measure groundwater levels. So here we are below the ground. I've labeled both a tree trunk, and these are the roots below the land surface. And so in this well is dug to a certain depth. And nested piezometers are when there are a series of piezometers very close to each other, so they're snug together like birds in a nest. So this is what a nested piezometer looks like, and I want you to imagine, you've seen these in different places, like at old former gas stations where they've drilled to see if there's been groundwater contamination. They drill a number of wells at different depths, and these are called nested piezometers. So these nested piezometers are all drilled in a place with the same surface elevation. So here is our surface elevation. And in this problem, we're going to use basic information that you would collect in the field to be able to calculate the hydraulic gradient or groundwater gradient in these nested piezometers. So some things we know about these wells are the surface elevation. So the surface elevation in this problem is 225 meters. And we can label each of these wells A, B, and C. So A is the deepest and C is the shallowest. And during the drilling, we measured how deep we drilled these piezometers. So this is the piezometer depth. And in this problem, I'll be kind of working through what is a kind of a table, basically. And so we have for piezometer A, B, and C. And so for A, our depth in meters is 150 meters. Our depth for B is 100, and our depth of C is 75. So this is all field observable information. The third piece of field observable information is our depth to water. So by depth to water, which is sometimes short form is DTW, and this is also in meters, is the depth of the water table below the land surface. So if we measure the water table here, and we can measure this using basically a measuring tape that you stick down the well, and you can record the depth to water. That is this distance here. So DTW is here. So our DTW for well A is 80 meters. And for well B is 77 meters, and for well C is 60 meters. So we can think of this as a little table that we're going to fill out as we go through this problem. So the first thing we want to calculate is the hydraulic head. So hydraulic head is, as we've talked about in class, the sum of pressure head and elevation head. So hydraulic head often has a symbol of H, or sorry, that should be small h. And using the information that we have here, we can calculate that as the surface elevation minus the depth to water. And so for A, for example, this would be, so H is equal to 225 minus 80, which is equal to 145 meters. And then similarly for B is 148. And I'm going to leave C blank so that you can calculate it on your own. So this hydraulic head is shows up here as the total elevation of the water table in relation to mean sea level or some other datum. So we have down here a datum, and so that's often mean sea level. And we're measuring relative to that, and the total height of the water table above mean sea level is the hydraulic head that we've just calculated. The second thing we want to be able to do is calculate the different components of hydraulic head, and those different components are pressure head and elevation head. So pressure head is also solvable using the information we have. So pressure head has different symbols. In our class, we often use P over rho g for pressure head. And in this example, it can be calculated as the depth of the piezometer minus the depth of water. And so again, kind of calculating this for each of these piezometers, we can get a result of 150 meters minus 80, which equals 70 meters. I'll leave B blank this time for you to calculate. And for C, we get a result of 15 meters. So that's the first component of hydraulic head. The second component of hydraulic head is elevation head. And the symbol for that most often is Z or Z. And elevation head is the surface elevation minus the depth of the piezometer. And so how to calculate that, we get a result of 225 minus 150, which is equal to 75 meters, or 125 meters for B, and I'll leave C blank for you to play with. So the last and most important thing we want to calculate is the actual hydraulic gradient. But before we do that, I want to take a small moment to, on the diagram over here, kind of break down more visually where hydraulic head, pressure head, and elevation head come in. So first of all, pressure head is the elevation difference between the bottom of the well and the water table. So this is the height of the water rising in the well. So this is P over rho g. Whereas Z is the elevation difference between the bottom of the well or the well screen and the datum. So we sum those two together to get our total hydraulic head. Now what we're calculating is the difference in hydraulic heads in different wells. So we calculated the hydraulic head of 145, 148 in A and B. I said I was going to leave C for you here, but I'll just tell you as a hint, it's a little bit higher. And what we're going to calculate is the difference between that hydraulic head over the change in height. So our equation for hydraulic gradient, or vertical hydraulic gradient, is dH dl. And our dH, if we're looking for the gradient between well A and well B, is here. Or sorry, excuse me, is between here and here. So here's our dH. And our dl is the difference between these two screens. So to calculate then, that would be h of b minus h of a, all divided by z of b minus z of a, which is equal to 148 minus 145 over 125 minus 75. That results in a gradient of 0.06. So what does this hydraulic gradient really mean? So we can see from this image here that our total head at greater depths is less than our total head at shallower depths. So what that means is that the gradient is upwards, which implies the flow is downwards because of Darcy's law. So as homework and for fun, you can fill in these blanks, but I'll also ask you two more questions. The first is, can you calculate the hydraulic gradient between B and C? And the second is this situation and is this tree and this bird sitting in this nest likely in a recharge area or a discharge area? And I'll leave it with that.